Well, up until this point in our videotapes, we've concentrated pretty much on describing the shape of objects. But more than half the job is to describe the size of objects, and we do this with dimensioning. Now, over the years, a lot of standards have evolved so that people, no matter where they're interpreting the drawings, will get the same interpretation. So, we'll start out by describing some of the key terms that everybody uses regarding dimensioning. Then we'll talk about some of the basic principles of good dimensioning, and we'll look at some examples and discuss how you can check dimensions once they're in place. And you might want to pay attention because there may be a quiz before we're done. Before we review the key terms used in dimensioning, let me just show you an example from my archives. Actually, this drawing was made when I was about 21 years old, working in my second job as a drafter in a screen products company in Caldwell, New Jersey. This happens to be an assembly drawing of a small hydraulic filter. And the assembly drawing, by the way, is used to show how people to put the parts together, not to show them how to build the parts. But even on the assembly drawing, you'll see that there are reference dimensions and there are an awful lot of notes. Let me show you the detailed drawing that actually shows the dimensions for just one of the parts of this assembly. And you can see for just a little part of an assembly, there are an awful lot of dimensions involved. And more than just dimensions, there are tolerances, there are little marks that show how smooth to make things. Sometimes there'll be marks to show how square to make things. And I have to tell you that once you've finished your orthographic drawings, as far as the shape description is concerned, your job is not even half done. At least half or maybe more than half the work in most instances is putting the dimensions on the drawing. So let's review some of the key terms related to adding dimensions to drawings. Engineering drawing is like pretty much any other business or subject that you can get involved in that you need to know the basic vocabulary before you can tell people about things or understand things. So let's review some of the key words involved in dimensioning. First of all, the dimension itself. A dimension is a numerical value shown on a drawing, and it defines the size of an object. Let me show you an example. Here you see the dimension, and the dimension itself is just the value. We'll talk about all these other things here in just a bit. But the dimension is the value that describes the size of some feature of an object. The dimension line is a thin, solid line used to show the extent and direction of a dimension. Now, there are two line weights used on drawings. There are thin lines and thick lines. Don't be fooled into thinking there are light lines and dark lines. They're not. They're all equally dark. Some are thinner and some are thicker. And the dimension line is one of the thin ones. And here you see part of the dimension line. Here you see the other part of the dimension line. And usually there's a break in a dimension line for the dimension value itself. Next, we need to talk about extension lines. Extension lines are thin, solid lines drawn perpendicular to dimension lines, and they show exactly where the dimension is referring to as far as the object goes. Here's an extension line, and on the other side is another extension line. By the way, sometimes you'll see these referred to also as witness lines. But if you see somebody, or if you see in a book someplace somebody referring to witness lines, you know they're talking about extension lines. The two words mean the same. So the extension lines show the extent of the dimension, and they're always drawn perpendicular to the dimension line itself. At the end of the dimension line, we find arrowheads. Arrowheads are placed at the ends of dimension lines to show the limits of the dimension. And you'll actually see two different styles of arrowheads on different drawings. They'll either be filled or they'll be open. Now, I'm talking about mechanical drawing, remember. If you're in the architectural drawing business, you may find them using dots or slashes or something else. Mechanical drawing always uses arrowheads. It's a matter of personal preference sometimes whether you use filled arrowheads or open arrowheads. My personal preference happens to be filled arrowheads, and I'll tell you why. If you use the open style arrowheads, what happens, I have to back up and recall that no one ever looks at an original drawing. They only look at copies of the drawings. So what happens in the copying process when you use open arrowheads is they'll start to fill in, and each one will fill in slightly differently, and so the arrowheads will all look different. If they're already filled in, the copying process will keep them filled in, and they'll look more uniform. Just a matter of personal taste on the business of open or filled arrowheads. Let's talk about leader lines. Take me to your leader line. A leader line is a thin, solid line used to direct dimensions or notes to the appropriate feature. Here's an example of a leader line being used to dimension this little fillet radius in here. The leader line includes the thin solid line with an arrowhead showing what it's leading to, and a little flag showing the words or the dimension or the notes or whatever that's being led by the leader line. In this case, it's a radius dimension. So leader lines are used to point out different features or sometimes dimensions on objects. Well, we're talking about the radius. Let's talk about a radius. A radius is the distance from the center of an arc to the arc itself. And there's a particular way we put radius dimensions on drawings these days. In the old days, you might see drawings that have a numerical value followed by the letter R. That's no longer true. If you're following the ANSI standards, the symbol for radius, which is the letter R, a capital R, the symbol for the radius is preceding the numerical value. So in this case, we say R and then the numeric value for radius. And similarly, we dimension diameters. A diameter is the distance from one side of a circle through the center to the opposite side. Here's an example of dimensioning a diameter. In this case, we're using a leader line again. And now, in the standards currently, we use a diameter symbol, which is the Greek letter phi, this little circle with a slash through it. And as is the case with the radius dimension, the symbol precedes the numerical value. So we have the diameter symbol followed by the numerical value. In this case, we're using a single arrow. We'll show you a little later how diameters might be dimensioned in the longitudinal view. In that case, we have a standard broken dimension line with 2 arrows. But in either case, we use the diameter symbol followed by the numerical value. It's actually impossible to manufacture anything exactly to a particular dimension. You think you can make a 1/2-inch diameter hole, and you think you're very good at making precision holes. Well, now, no matter how good a machinist you are, if I get a bigger magnifying glass or a bigger microscope or an electron beam microscope, I'll find that 1/2 inch is a molecule off this way or that way. There is no such thing as a precise dimension. So we need to have something called a tolerance, and every dimension on a drawing will have a tolerance. The tolerance is the difference between the maximum and minimum permitted sizes. Some people would say the tolerance describes the difference between the maximum and minimum material conditions. Let's see an example of that. Here is one way to specify a tolerance. Here we specified a dimension, and instead of giving a single number, we've given an upper limit and a lower limit. And what this means is that when you actually manufacture this part, there are lots of acceptable parts as long as the measured value of the finished part is between the upper and lower limits. The tolerance itself is actually the difference between the maximum and minimum allowable sizes. In this example, the upper limit is 1.510, the lower limit is 1.490. If we do a little arithmetic, we find the difference is 0.020, or a machinist would say 20 thousandths of an inch. So the tolerance in this case is 20 thousandths. Now, the limit dimension is one way to specify a tolerance. You'll also see tolerances specified by given a nominal value followed by plus something and minus something. Or in many cases, you'll see the tolerance is specified by simply placing a nominal value. In this case, it might be 1.5 inches. But then in the title block, you'll find a little note that will say something like, unless otherwise specified, all 3-place decimal dimensions have a tolerance of plus or minus 10 thousandths. Or there may be a whole list of these. It may say all 2-place decimal dimensions have a tolerance of plus or minus 20 thousandths. Or maybe it'll say all 4-place decimal dimensions have a tolerance of such and such. But in any case, every number on every drawing has to have a tolerance, and it must be specified either in a note or as a limit dimension or as a plus or minus tolerance dimension. Well, now that we have some common understanding of the basic vocabulary of dimensioning, we can talk about the principles of good dimensioning. There is one overriding principle that comes before any of the 20 principles I'm going to describe, and that is clarity. The reason that we have dimensioning and the reason that we have principles of dimensioning is because we want to, as clearly as possible, define the sizes of objects. And so all of this was invented to create very clear, precise communication about sizes of objects. Let's talk about some of the principles of good dimensioning. Principle number 1. Each feature of an object is dimensioned once and only once. Now here's an example where we've dimensioned the height of the object, and actually we've dimensioned it twice. You notice that you can get the overall height here, or you can add these two dimensions. This is a problem if you put both of these in there. And we're going to leave one of these out. The reason is because of the tolerances. Suppose that I put that back for a minute. Suppose that we dimensioned with what most people would consider double dimensioning. Suppose we put these double dimensions in here. How tall can this object be? Well, let's say that they all use the standard tolerance from a title block note that says plus or minus 10 thousandths. That means that the overall height of this object, according to the large dimension here, is plus or minus 10 thousandths. However, if you add this one, the step here, and suppose it was as big as you could allow, plus 10 thousandths, but suppose this part was as big as you could allow, plus 10 thousandths, now you have a problem, because if you add these two up, you can have this 20 thousandths larger than the average. And so what's the machinist to do? Is he to go by adding the sum of these stacked dimensions or the overall? We don't want to give him a choice because he'll always choose opposite the way you want it. So we leave one of them out. So each feature of an object is dimensioned once and only once. If we have this little shelf here, we don't want to dimension it twice. If we have the height, we don't want to dimension it twice, just once. Next principle. Dimensions should be selected to suit the function of the object. And this is a tough one if you're a beginner, because in many cases you're doing these examples from books and you don't yet have enough experience to know exactly what the function of the object is. As you get experience, you'll know what the object's being used for. In this case, what's more important on this object? The height of this step or the depth of this little step? If we don't know, we have to make a guess, and unless you know the function, nobody can say your guess is wrong. The rule of thumb is dimension stuff instead of space. Remember, we don't want to put both of those in there. So in this case, we'll dimension the height of this feature rather than the depth of that step. There may be a part where the depth is more important, and remember, this tolerance buildup will cause us problems if we don't dimension it properly. Next principle. Dimension should be placed in the most descriptive view of the feature being dimensioned. Now take a look at this object. We have two choices here. We can either dimension the front view or we can dimension the right side view. Both of those are dimensioning the same feature. But which of these views more clearly describes the feature being dimensioned? Well, when I challenge my students to this and I ask them to point out what this dimension is really showing, they almost all automatically go to the front view. That's the more descriptive view of that feature. Here you can't, in the side view, you cannot tell whether it's an innie or an outie. So we're not going to dimension it there. The principle says dimension should be placed in the most descriptive view of the feature being dimensioned. And you need to pay attention to this one because in the past, students miss this principle more than any others. Principle 4. Dimension should specify only the size of a feature, not the manufacturing method. Now, you may find some old textbooks that have a dimension like this for a hole. Such and such size drill. Well, you need to keep in mind that engineering drawings, once they're signed off, become legal documents, and they have to be followed exactly. So you don't really care whether the machinist uses a drill to make this hole, or uses a laser, or a water jet, or one of them metal-eating beavers. You don't really care. Don't tell them how to do it. Just tell the size. In this case, diameter 1 inch. If you specify the manufacturing processes, they have no choice. There may be times when the manufacturing process is extremely important, then you put it on. But in general, you dimension sizes, you don't tell them how to make it. Now, let's talk about angles on drawings. All of these right angles on drawings do not have to be dimensioned. Angles shown on drawings as right angles are assumed to be 90 degrees unless otherwise specified and need not be dimensioned. However, whenever you have an angle that's not 90 degrees, you must put a dimension in. Dimensions should be located outside the boundaries of the object whenever possible. Now, on a simple drawing, you would not confuse anybody if you put this dimension right there on the drawing itself, but it's not a good practice. As soon as you get to real parts, as soon as there's any complexity at all, if people start putting dimensions on the drawing itself, pretty soon you won't be able to tell what's the object and what's the dimension. So we keep the dimensions away from the definition of the shape of the object. We keep it off the object and use extension lines to move it out. Dimension lines should be aligned and grouped where possible to promote clarity and uniform appearance. And here we have this little step, and we're just dimensioning the width in this case. Of course, there are more dimensions before we're done and more views before we're done. But here we have a nice little grouping of dimensions. And if the machinist is going to set up to mill the steps on there, he or she only has one place to look to get all the information, and that's good. A not so good thing would be to dimension this way. Now, mathematicians would say this is equal, but we're not in math class. We're in engineering drawing class. Cross-dimension lines should be avoided whenever possible. Notice here that this extension line is crossing that dimension line. I have some instructor friends who would get out their red ink and bleed all over your drawing if you put that kind of thing on a drawing. Here's a case where the extension lines run across the object and the dimensions placed off the object. But we can avoid this. Now, there are times when you cannot avoid running extension lines across an object, but there are many times when you can. Most of the time you can. The trick is, when you're dimensioning, is go from in to out. Because if you dimension the overall dimension first, you won't have left yourself enough room, and then you'll be tempted to do this double cross trick, which is uncool. We don't like to do that. Now, regarding the spacing between the object and the dimension lines. The space between the first dimension line and the object should be at least 3/8 of an inch, which is the same as 10 millimeters. We're talking about the first dimension line here and the space here between the object and the first dimension line. Notice that that's at least, that's a minimum. It's not always 3/8, but you need to have at least 3/8. Otherwise it gets crowded here and it's harder to read. When we're dimensioning the stacked dimensions like this, the space between dimensions should be at least 1/4 of an inch, alias 6 millimeters. And by the way, if we were using limit dimensions and we had a number over a number and a number over a number, we may need more space than that. This again is a minimum amount of space between dimensions. Now let's talk about how we deal with the ends of extension lines. There should be a visible gap between the object and the origin of an extension line. There's a little visible gap there. Nowadays, when we're using more and more computer-aided design software, sometimes we're hamstrung by the computer science majors who write the code for some of these. As a matter of fact, I was looking at a $4,000 per copy piece of CAD software just the other day, and it did not leave any visible gaps here. And there wasn't anything I could do about it except go buy a different piece of software. But if you're drawing with manual tools, you need to know about this. Leave a visible gap, about a 32nd of an inch. The gap also should be uniform, wherever possible. Then the next question is, on this extension line, how far do you dangle it out beyond the dimension line? And the rule of thumb is extension line should extend about 1/8 of an inch beyond the last dimension line. Nothing magic about that. If I was grading your drawing, I wouldn't lay my scale and make sure that you did it exactly 1/8 of an inch. However, if you had one of these dangling out 1/32 of an inch and another one dangling out 1.5 inches, I would say sloppy. And by the way, neatness counts in this business, because unless you're very neat, you're not very precise, and people will misinterpret the drawing, and that can cause disasters. I break for arrowheads. Extension lines should be broken if they cross or if they're close to an arrowhead. Here we have these extension lines coming up here, and it may be hard to see on the TV camera, but there's a little break in these extension lines to make room for that arrowhead. Again, we're just trying to keep it neat and tidy and to promote clarity with these principles. Now, let's talk about leader lines used to dimension circles or arcs. They should be radial. That means they should point to the center of the circle. Now, they don't go through to the center of the circle, but if you chase this leader line all the way along, it should strike the center of the circle. Here's one that hits a glancing blow. Wrong. You must have leader lines that are radial lines. That is, if they were continued, they would hit the center of the circle. Now, nowadays, with the current standards, dimensions should be oriented to be read from the bottom of the drawing. This is known as unidirectional dimensioning. In the old days, and in some of the textbooks, you'll still see examples where they use the aligned method. In this case, the text for this dimension is lined up with a dimension line. That was very common, but not anymore. That was common in days gone by. The new standards say that we use unidirectional dimensioning. Once again about diameters. Diameters are dimensioned with a numerical value preceded by the diameter symbol. And here we see the leader, radial line, diameter symbol followed by numerical value. Now, what happens when we have a lot of concentric circles to dimension? Here's a principle that sometimes you see violated in a lot of the textbook examples. Concentric circles should be dimensioned in a longitudinal or rectangular view whenever possible. The alternative to doing this is to crisscross all these diameter dimensions right here on the circular view, and that violates the principle about keeping dimensions off the object. And if you get very many of them on there, like here we have 3 or 4 to put on, they start getting harder and harder to read. So he put them in the longitudinal view. But why did I dimension this hole over here, you ask? Well, because the hole is hidden in the right side view, and we do not dimension things where they're hidden. Remember, we dimension things in the most descriptive view of the feature. Now, we could change this to a right side section view, and in that case it would be perfectly fine to move the whole dimension diameter also over here to the longitudinal view. Radii are dimensioned with a numerical value preceded by the radius symbol, and you saw that before. Here we have the leader line, the radius symbol R, followed by the numeric value. Notice that there's no center point given for the radius in this case, and the reason is because these two lines that are at 90 degrees to each other are tangent to that arc, and there's only one place that the center of that arc can be. If you just tell them the radius and they know the place to put these lines, they will have no problem in figuring out where the center of that radius arc is. However, in some cases, like this case, there's no hint from the geometry as to where the center of this radius is. And in that case, when a dimension is given to the center of an arc or radius, a small little cross is shown at the center. So we put a little plus sign there, and then we use that plus sign to actually dimension the location, in this case horizontally and vertically, the location of the center of that radius. We still have the leader line as a radial line, and the radius symbol followed by the numerical value. So whenever we have a radius and you cannot locate the center from the given geometry, you must put the little plus and add the dimensions to locate the center of the arc. Now let's talk about this kind of hole, which is 2 holes in one. There's a small through hole and there's this bigger hole that only goes down a certain way. It's called a counterbore, and there's even special tools to make counterbored holes. And the way we dimension this kind of thing is in a note. Counterbored or spot-faced. A spot face is similar to a counterbore, but it's just deep enough to clean a rough surface. Counterbore or spot face or countersunk. A countersunk is at an angle rather than a right angle step here. All of those type holes should be specified in a note. But here we have the diameter symbol followed by the numerical value for the dimension. That diameter is for the through hole, the small hole that goes all the way through. And then right underneath that, with the same leader, we have the counterbored symbol. It's one of the ANSI standard symbols, followed by the diameter symbol, and then the size of the diameter, followed by a depth symbol and the dimension for the depth. The depth is how far it is from the surface down to the extent of that counterbore diameter. So these are done in a note rather than dimensioning these separately with separate diameters and then coming off here and just doing a vertical dimension. All in one note. Another reason for putting them all in one place is the machinist is going to do this as one process, and you don't want to have them playing the Trivial Pursuits dimensioning exercise just to find all the information about that counterbore hole. Putting it all in one note makes it easier for the machinist and promotes clarity. Now, let's talk about blind holes. What's a blind hole? Well, if you held this block up to the light, you could not see through it. You'd be blind. This hole does not go all the way through, but it's a drilled hole. It's very expensive to make a flat bottom hole. So the question is, when we specify the diameter and depth, and by the way, we do that in a note again. It says diameter symbol, dimension, depth symbol, dimension. In that note, what are we talking about when we say how deep to make that? What we're talking about is the actual depth of the full diameter. The question is, what part of that hole is this depth? The depth of a blind hole is the depth of the full diameter measured from the surface of the object. In other words, when we look at this depth dimension, we're looking at the specified depth from the surface down as deep as the full diameter part goes, not the little pointy thing. It's possible, by the way, to make flat bottom holes, but they're expensive. Usually we drill a hole with a pointy drill, and the actual angle on that drill will even vary depending on whether we sharpen the drill for wood or plastic or metal or cast iron or kryptonite or whatever. But in any case, we don't care how much is hanging out. When we dimension this, we only care about the full diameter depth. Remember, sometimes when you're dimensioning, it may seem that you're caught in a catch-22, that some of these principles will conflict with other principles, but you always fall back on the overriding principle of dimensioning. The overriding principle is that of clarity. Our whole purpose for doing this is to, as clearly as possible, specify the exact size of objects. Well, now that we've discussed some of the key words and we looked at the basic principles of good dimensioning, you should be ready for a quiz. You didn't think you were going to get through this without a quiz, did you? Well, I had my phony student, Ferd Snodfield, put together a dimension drawing for us for this quiz. And actually I had them put letters on here instead of numbers so we could go through and talk about which, if any, of these dimensions might violate some of the principles of good dimensioning. Let's take a look at the dimensions on this drawing, and let's just plow through in alphabetical order from A through whatever and discuss each dimension in turn. Here's dimension A. What do you think it's dimensioning, and do you think it's violating any of the principles of good dimensioning? Now, this is your time to get involved. Back there, next to the last row, third from the left. What is it? You say you don't like this one? Why not? You're right. What is it dimensioning? It's dimensioning the location of the center of this hole. And the hole is showing up hidden here. And principle 3, remember the principles by the number, principle 3 says we dimension in the most descriptive view of the feature being dimensioned. And this is not the most descriptive view of the hole. So we want to locate the hole where it looks like a hole. Dimension A needs to be fixed. How about dimension B? That's dimensioning the other orientation. I mean, we have to go both width-wise and depth-wise to locate the center of that hole. And this is locating depth-wise the center of the hole. But what do you think of that one? Too easy. Crowded. Remember, the minimum spacing here should have been 3/8. You don't know how big this drawing actually was made when it was made, but no matter how big it was made, there's not enough space there for dimension B. How about dimension C? Dimensioning what? Depth of the object. It's okay to dimension depth in a top view? Sure. Is it okay to dimension it in the side view? Yeah. So we could choose. If the spacing here was enough to make room for B, then C would be okay. Where's D? D is right here in the top view, dimensioning the width of that little feature there. Is that okay? Why not? What's it dimensioning? And immediately you look here in the front view, you say it's dimensioning the width of that prong sticking up there, and the front view is more descriptive than the top view. So dimension D should have been placed in the front view. What about dimension E?